us were very excited about the power of AI agents. In particular, we started in June 2026. And our interest was driven by some recent papers from DeepMind, Fund Search, which demonstrated early on that you can use AI to improve the state-of-the-art performance of algorithms, and then was followed by AlphaEvolve, showing that coding agents can be used to improve the SOTA for some existing systems and techniques. And then OpenEvolve was an open source version of AlphaEvolve, which was released around the same time. And obviously, we have all these kind of agents, coding agents like Claude, Codex, and Cursor. Triggered by this kind of events, we started to run a special seminar over the last summer at Berkeley, and where the students, system students, were using this AI evolutionary agents to apply it to their own system, to their own research. And in particular, we went through 12 different projects.
Good here?
Yeah. And the results were quite impressive, or better than expected. So these 12 projects included around 7 published work by the students in top conferences in systems or AI, included also some work in progress and some publication, some research just published on arXiv. And in 10 out of these 12 cases, we got results which are better than SOTA. And not only that, but it was very cheap to use, the best models than Gemini and OpenAI and GPT to get the results. So it was quite cheap and quite fast. So this a lot of excitements, and also since then. And we done a lot of work in the space. In particular, we taught 2 graduate courses, the previous 2 semesters. We wrote position papers. We launched the ADRS blog series, where ADRS stands for AI-driven research for systems. And of course, we are from academia, so we published and we build a bunch of systems and publish a bunch of papers. So everything started with great expectations, and the expectation was that AI will disrupt the system research the way we know it. So what happened actually over the past year? What was our experience? So what was reality? Well, it is true that AI did improve our research productivity. It's great, has been great for research, providing some ideas, of course, for speeding up some paper writing. So no question, has a very positive impact on our productivity. It did also become a big part of our research agenda, like I just mentioned early on. However, did it really disrupt the way we do the research? Did it allow us to build new production systems in a fraction of time we used to do? Did it allow us to come with new research, truly new research ideas? Well, the answer to those, no, not yet. So this talk is about trying to understand why, what are the limitations we encountered. And I would say this is not only our story, but the story of many others, people we talked with for the past several months. Now, if you take a step back, the key goal of an AI coding agent is to develop a software system that meets a certain level of assurance with acceptable levels of risks as fast as possible and as cheaply as possible. Here, the software assurance is an ongoing process to establish and maintain some justified confidence, which is supported by credible evidence from running the software, that the software system will satisfy some specific claims, will have some specific properties, and in its deployment environment. So fundamentally, you need to do that by using the resources at your disposal. And the resources come in three forms. It's humans, agents, AI agents, and of course, compute. So the question is how to achieve our goal by best using these resources. And if you think about this as a framework or as a system, then the key question to answer is about what are the bottlenecks. And then once you identify the bottlenecks, you alleviate them or you remove them if you can, and then you are going to speed up the development. So let me start with the motivating examples. So this is work we done recently, and the goal here is to synthesize a key value storage system from scratch. And as everyone knows, it's a pretty simple system, pretty simple interface actually, where you associate a key with a value and you put that per key value in the storage, and then you can, given the key, you can retrieve the value. And in this particular case, it was a pretty simple setting. We have only one server, so no distributed environment. Although the server was multi-threaded, so you have concurrency. So basically, you store the data on the disk and you cache in memory to retrieve it faster. And the goal was to maximize the throughput, and to evaluate it, we use this YCSB, which is a well-known benchmark for such workloads. So now in the process of using these evolutionary AI agents to synthesize the solution, we got one solution at some point which was 6 times faster than all the previous solutions, a huge improvement. So why was that, right? Of course, you are curious to understand what led to such a big improvement. Well, it turns out that these benchmarks generated values in a predictable way. So when you generate the value in the benchmark, you need to say what the value it is. And in this particular case, you generated the value by hashing from the key associated with that value and a seed. Now, the agent found this out. So, and instead of storing the values, it basically computed the values using this predictive function on the fly. Which means that because you don't need to store up the values, you only need to store up only the keys, you can store a lot of more items in memory, so the retrieve is going to be much faster, hence the improvement we've seen. Now, everyone knows this is kind of reward hacking. So if you look about this reward hacking, you see it's due to two gaps, and this is the main topics of my talks. One gap, we call it requirement gap. So you see in this case, the agent in the specification was required to return a value which was put associated with a particular key. However, the user intent, the stakeholders we are going to call intent, was to store that value, right? Not only to return that value. So here is a gap. And then there is a model gap in this particular based on the workload in the development versus deployment environment. In the benchmark in the development environment contains predictable values. However, in the real world, the deployment, you have arbitrary values. So here is another gap. So now, how is the solution typically working in this case? So let's just take a step back here. So you have a bunch of requirements, which basically describe the system needs to be built, performance goals, and so forth. And you have a model which tries to abstract away the deployment environment. And this is about where in the environment you are going to target the deployment, the workload, which you think is representative of the real workload, kind of the failures and things like that. And now a developer or an AI agent takes these requirements and the model and generates a program. And then this program is evaluated. Right? And evaluated, you can have unit test, end-to-end test, integration test, or you can have contracts or formal method. Now, if it passes this evaluation, or if it is an evaluation, it doesn't pass, then you provide the feedback to the developer and to the AI agents, And then you are going to continue in a loop until the program passes the evaluation, and then you are going to deploy it. The problem is, again, that the requirements and the models are an abstractions. On one hand, of the user intent, what the user wanted the system to do, and the real world where the system is going to be deployed. And these are the delta between those are the requirement gaps you are talking about. So being a little bit more specific, the requirement gap is there because the intent of the users is broader than the requirement. And here are some examples. There are omissions, things that the system should do, but is not specified, like store arbitrary client values. There are exclusions, like things systems should not do and are not specified, like never expose customer data. Trade-offs, like for instance, a search has a 200 millisecond SLA. If this SLA is exceeded, if this deadline is exceeded, should you wait? Should you return partial results, or you should return a failure? And there are conflicts which are not specified how to be solved. Like for instance, you want personalization, but this needs chat history, but privacy rules prohibit retaining the chat history. How you are going to resolve this trade-off? It has to be specified. Now, the model gap is the same you have for the same reason, because the real world is broader than the model. The model gap, so there are examples are the workload predictable. For instance, the workloads have predictable benchmarks during the development versus arbitrary development, arbitrary values during the deployment. You have failures like fail stop tests during the testing and Byzantine false during the deployment. You have dependencies like setable mocks versus changing the APIs in the physical, in the deployment case. Or you can have adversary and drift, new attacks or workloads, which happens after release. So these two gaps are responsible for the reward hacking, and the reward hacking is arguably responsible for many of the things you have seen recently in the news, like these agents escaping their environments and going rogue. It's also, you can trace back them to alignments or misalignments and hallucinations. And a key challenge here is about underrepresentation. Because you can only judge from available evidence, and the evidence is often incomplete. New evidence might invalidate acceptance of a program P during deployment. Examples are implementation P developed, is an implementation developed in, under the model M, which assume first of failures. Then you deploy this in practice, and as long as you have only first of failures in the deployment environment, you are good. The stakeholder accept the implementation, but once you get a failure, like a Byzantine failure, like a corrupted memory, that's no longer acceptable. Now, why is closing these requirements gaps are hard? So first of all, intent might be tacit, contested, or changing. Fundamentally, you don't know what you don't know, right? You cannot think about all the corner or future cases until you see them, right? And this has been noticed for the past decades in many domains: software engineering, AI, economics with contracts, politics, and so forth. And you can also think about this like from a pure solution perspective. If you think about how you can close them, well, one way is to ask people whenever there is many material change on the deployment, you can ask people, is this good or not? Or you can create an oracle, a model or a simulator that predicts every material judgment of the stakeholder. The same is true with a model. The model, if you really think about you want a good model, you need to prove that every omitted aspect from the real world in the model, what the model is misses, is irrelevant for acceptability of that implementation. And you keep the claim, and the other one, the claims have to be valid as the world changes. Okay, and again, has been a lot of work here over the past decades pointing out to this point and this kind of fundamental gap between the model used in development and the real world. Okay, so again, here to illustrate why it's hard, you can ask people, for instance, to every time on the changing environment to say, okay, is this change materially important for the model you are going to have? Or you can predict, you can simulate the real world, right? But obviously, all this direct giving the user direct access and having complete simulations are not feasible. Actually, even if you have the direct access, it's on one hand, the cost and latency can be prohibitive, but on the other hand, it's like you only can reason for the existing evidence. You cannot reason for things you have never seen it, you haven't thought about. And obviously for the model, for the deployment, for the real world, you can have a complete simulation. You can think to have a simulation, but once you have the simulation, that's another model. So you are back in square one because you need to demonstrate that the simulation, there is no gap between that simulation and the real world. Now, the other thing I want to make is that now why we are talking about this, because we have been, like I said, these gaps are there and have been there for decades. People identify them, recognize them. Well, one reason we are emphasizing this because agents amplify the gaps. And these are for several reasons. It's context asymmetry. A developer typically has more local and system and organizational context about a task than the agent, which brings broader context, but has less specific context about that task. The other one, which is very important, AI iterates much faster under a fixed requirements model and a fixed evaluator, which means they discover and exploit the exploitations much faster. Actually, the developers typically give up, or they are not to find any of this exploitation, even if they want. But the model, because AI agent is much faster, they are going to find it, what humans will never find. And its deployment scale, especially if you are going now to have an automatic deployment of these programs in production. Let me skip. Now, I want to say about there is a third gap, and which I want to mention and this is between the evaluator and the requirement on one side and requirement and model on the other side. So the question, this gaps, it's illustrated illustrate this gap is that you have an evaluator. So, but passing this evaluator, does it guarantee that the implementation is going to satisfy our requirements under model, right? In all possible executions. And in general, the answer is no, because for instance, you use kind of unit tests and so forth, so it's only a subset of tests. You can show that for these points, for these data points, for these values, you satisfy the requirements under RAM. But actually, there are ways you can do it and you close the gap, and this is formal methods. And that's why we are not focusing as much on this gap right now. However, the reason I'm mentioning this gap is because using the formal specs actually can widen requirements and model gaps, because the formal specs are going to be less expressive, say, than kind of natural language written requirements and the models. So finally, like I will say, does narrowing these gaps help? Yes, most successes reported so far are in domains with narrower gaps. And there are significant ongoing work to narrow gaps in other domains. And here are some examples. Formal mathematics. In formal mathematics, model gaps is closed because there you have formal semantics, you have axiomatic systems, which fully defined the world in which the properties have to be it needs to be true. The theorem has to be true. The requirement gap still remains because informal to formal translation still remains, capturing what is your intent in a theorem and so forth. Hardware systems. For hardware system, you have instruction set architecture, you have RTL, which bounds the relevant behavior. Of course, this doesn't close the gap to physical effects, which are remaining outside the model. Strong verification also may close the evaluation gap. System optimization. We are talking about system optimization versus system synthesis. With system optimization, you are going to be anchored in a code. And in this code is going to capture the interfaces, edge cases, functionality. So it's kind of narrowing model and requirement gaps as compared with the system synthesis, which lacks this anchor and must infer more from incomplete requirements and models. And finally, reward models, right? What reward models try to achieve is to narrow the model gap by learning the models, part of the model, by interacting with the deployment work. Okay, so 2 more minutes and I'll be done. So how can you close this gap in general? Well, to close this gap in general, you need another loop, which actually includes the intent, the user intent, and the real world. And this is the first step here, is to have observe and try to detect what are kind of the issues, unexpected issues, misbehaviors. Then you need to diagnose them. Then you need to revise, and you are going to revise the requirements, hopefully improve the requirements, improve the models, improve the evaluators, which will reduce the gaps. And you do this until you are going to achieve, you are assured your level of assurance and risks. And let me give back, because I'm so, skip a few slides. So we've done quite a bit of work in this area, but of course, much more remains to be done. And here are some pieces of work we've done, for instance, for the loop, for development loop, evolutionary loop, for AI agents, for reducing the evaluation gap, for diagnosing, tracing the intent of, and from the traces, which represents the user interaction with the systems or the agent interaction with the real world, and obviously directly trying to reduce the, to narrow the requirements, the model gaps. So what are the takeaways? So here, the takeaways from this presentation. First, the model and requirement gaps are fundamental and cannot be certified as closed in an open and changing environment. Again, because you don't know what you don't know. So therefore, you can only narrow them. The second one is like the humans will remain in the assurance loop because they are needed at least to narrow the requirement gap because they own the intent. And likely because they are going to be in this assurance loop, they are going to be the bottleneck. And the evaluation gap can be closed using formal method, but the cost can be increasing the model and requirement gaps because the lack or the limited expressivity of the specifications which are needed by the formal method. Finally, these are not new problems, like I mentioned. However, AI agent exacerbates them because of the context asymmetry, speed, and scale. They are going to find and exploit this kind of gaps much better, much faster than humans. So therefore, what do we need to do? We need to use the best practices in software engineering and security, and we need to be more cautious and meticulous than ever before. And of course, do a lot of more and interesting research to close these gaps. Thank you.
Thank you so much for starting us off. What a wonderful talk. Next, we have Nick Harris. He's founder, CEO of Light Matter, and he'll be talking on photonics is the future of computing.
All right, looks like we're getting slides up. Great to be here at the Agentic AI Summit here at Berkeley. My first visit to Berkeley, I went to MIT. Lots of love for Berkeley, but yeah, good to be here. So today I'm going to be telling you about Light Matter and some of the stuff that we're doing. 10 minutes, so let's jump in. If you zoom out on what's happening in AI, and especially with the advent of agentic AI workloads, which I remember hearing about starting in 25, which felt pretty early, really what's going on is the world is undergoing a massive AI build out. We're building data centers in Texas and British Columbia that are using as much power as the biggest cities on Earth. Think about New York City, something like 7 gigawatts. That's going to be a pretty average data center in Texas, in Abilene. And why is this happening? Like, what's the motivation behind building these energy-consuming objects that have 100 times the density of a city? Why are we doing this? You can go to the next slide here. My clicker is not clicking. There we go. So here's why. If you look over the past several years at the runtime for AI models, how long can they run given a complex task and have a 50% chance of completing that task? That's been growing obviously exponentially. So now we're at a spot where the latest AI models can run for something like 24 hours and have a 50% chance of getting a problem solved. I don't know anybody who can work for 24 hours nonstop and have a 50% chance at solving a hard technical problem. Certainly I can't do it. And so we're on this trajectory. I can't see any saturation in the data, to be clear. We're on this trajectory where AI models are going to be solving harder and harder, longer time horizon problems, all in one go. So it's a pretty incredible capability that we're unlocking. And this is what's underlying the build out, the amount of energy that we're going to spend, all the buildings, the GPUs, the custom AI ASICs that are going to be going into these buildings. This is what underlies it. We're starting to be able to have machines perform calculations and solve problems that are incredibly hard for humans, and we're compressing the amount of time it takes to do very hard and valuable work. So there's one backdrop here to keep in mind. I'm in the hardware space. Lightmatter is building photonic interconnects that link up AI supercomputers. And one of the things we're tracking is the amount of power that's being used for building these systems. And you can see in the white curve, this is the frontier AI model power consumption curve versus the US energy grid growth rate. You're something like a few % per year growth in energy coming online in the US. And AI is really going to smash through what the US energy grid is going to be able to bring online. There's a lot of work on nuclear reactors. They'll have 100 megawatt nuclear reactors per gigawatt data center. I just want to think about a gigawatt with you for a second. A house is a few kilowatts. A rack is starting to be a megawatt. 1,000 racks is a gigawatt. This room could hold a few hundred racks. So you think about the energy density of what we're talking about. It's pretty incredible. So how are we going to close this gap? How are we going to let AI continue on this progress curve? I've got an idea, and I'll tell you all about it. So it turns out that interconnect is actually the principal challenge. How you allow GPUs and XPUs to communicate is the principal challenge today in enabling this roadmap for driving agentic AI workloads and enabling growth in the amount of computation that we can do. And that comes from first principles. But I'm going to jump to the conclusion first here, given a 10-minute talk. With ultra-fast interconnects, at Lightmatter we use light to connect GPUs and chips. We have single waveguides that transmit 1.6 terabit per second per optical fiber. That's 1,600 homes worth of bandwidth in a single optical fiber. What we're able to do is improve time to train by 3x. So the same number of GPUs running the same workload, 3 times faster time to train. So your data center finishes that training job for the next Fable model in 1/3 the time, and you can train maybe the next 2 versions over that month that you were planning to do. Significant improvements in prefill and decode. These are phases of inference, 3x for prefill and 11x interactivity, tokens per second per user for decode. So linking computer chips together, these XPUs, these GPUs using light, is going to deliver an enormous performance uplift for AI workloads. And why is this happening? What's the fundamental thing that we're driving towards? What does the photonic technology that we build at Lightmatter enable? It enables you to build gigantic computer systems that behave as a single brain. These are strong scaling systems in computer science, if you want to talk about it that way. Strong scaling systems. So normally, you've got 2 computer chips, and you'd like them to run a workload together, and you'd like to get 2 units of performance. And if I have 1,000, I'd like 1,000 units of performance. The challenge is that most workloads are not embarrassingly parallel. You can't run them in parallel like that. They need synchronization. They need to share parts of the operation. And so how do you build a computer that acts over 1,000 chips like a single chip? Well, at the limit, you want to have 0 latency in communicating between GPUs, and you want to have infinite bandwidth. If you had 0 latency and infinite bandwidth, well, there's really no difference between these GPUs that are many meters away. So that's what we do at Lightmatter. We build interconnects that are so blazingly fast. We already have chips that are 114 terabit per second. State of the art is about 10 terabit per second. We have fibers that are 1.6 terabit per second. State of the art is 0.2. There's 10x's all over the place. What we're doing is we are approximating this perfect interconnect and this perfectly strong scaling supercomputer. Over the next 2 years, you're going to see the first systems with 1,000 GPUs or XPUs communicating and acting as a single giant GPU or XPU. And this is going to drive those inference and training results that I talked about earlier. So this is what the tech looks like. This is one of our chips, M1000. It's the fastest optical communication device in the world, 114 terabit per second. You can see the optical fibers on the top and bottom. Each one of those fibers is moving 1.6 terabit per second of data. 1.6 houses. This chip moves 114,000 houses worth of bandwidth. That's how fast it is. The cables that connect North America to Europe are about 200 terabits. That's less than 2 of these chips. This is what's coming, and this is what's going to enable these very large AI supercomputers that act like a single chip. And I'll leave you with this. This is kind of what the systems look like. On the left, we're showing one of our M1000 racks. This single rack is several petabit per second of I/O. So the entire world's traffic, internet traffic, is a single rack from Lightmatter, M1000 there on the left. And we build out data centers today because one of the big challenges in computer science and scaling these AI workloads and AI platforms is reliability. You have, let's say, 100,000 GPUs in a data center and 10 million connections that are linking them together. Those 10 million connections, they better not have any errors. If there are errors, they're going to freeze the AI training workload run. They're going to crash your inference workload. We have to make sure that these systems are extremely reliable. And at Lightmatter, we build out entire validation data centers where we're operating hundreds to thousands of these platforms and proving that they just won't crash. They're going to be rock solid as they transport the kind of data on the scale of, the internet between the continents. And so with that, I'll thank you guys for the time, and I hope you enjoy the day today.
Thank you so much for that talk, Nick. Now we have Goisha Steiner, IBM Fellow, IBM Research, to talk beyond the harnesses, platform solutions, and agent reliability, security, and efficiency.
Thank you very much. It's great to be here. I believe we are entering the next wave of application platform evolution. The first wave being when we separated hardware from software and developed the first high-level programming languages. The second being cloud computing, when we started creating distributed applications across the data center and the globe. Both of these waves resulted in creating a new operating system. And by operating system, I mean a foundation that separates application from hardware, from infrastructure through a layer of abstraction, but also foundation that offers certain primitives that applications can rely on to achieve resiliency, scalability, and efficiency. AI applications are without any doubt the most non-deterministic and unreliable component that has ever been introduced in enterprise architectures, and I believe they will require a new foundation, a new operating system as well. Now, AI applications are applications. They can run on existing foundation. The problem really is that this foundation doesn't really do much to help solve the novel challenges that are occurring with these applications. And I personally like characterizing these challenges in two groups. There are structural and semantic. Structural challenges are because these applications have open-ended instruction set. By instruction set, I mean the set of operations that an agent can execute on an external world. They decide which of these instructions to use at runtime, and they order them at runtime. Now, that breaks a few very important assumptions that existing platforms make. Zero trust security becomes very difficult because zero trust security depends on understanding interaction patterns between applications a priori at configuration time. Recovery becomes very difficult because traditional techniques like compensations and rollback become intractable to implement. And of course, these applications are not fully testable in pre-deployment. Another problem is the lack of separation of instructions and data in the context, which is what agents are working off. That's why we are seeing so many novel security threats associated with agents. And agents communicate exchanging that context, so we are losing execution separation between different agents, and that essentially means that controlling blast radius of resiliency and security issues becomes very difficult. And now there comes this entire semantic side that Ion Stoica has been talking about, that we are not able to fully specify agent goals. It's very difficult to express what agents should do in a narrative, but it's even harder to specify what agents shouldn't do. And we still lack any formal methods of expressing agents' goals and validating agents' goals. It doesn't help that AI models, the agents, are not good in reporting on their own status. We essentially do not have any reliable error codes. All this means that understanding if agent is working correctly, if it's succeeding, detecting its failure, and understanding its liveness, so if it's making progress, if it's converging towards the goal or not hanging, all of these problems become very difficult. And if we cannot determine what the problem is, we cannot recover from this either. And of course, there is also a semantic gap between how agent is thinking and designing what it should be doing and the schema-based nature of real-world interfaces that with constantly changing interfaces leads to mismatch and new errors being introduced. So how do we address these problems today? Well, all of this is done in a bespoke manner in the application layer. So we develop frameworks, we develop harnesses, and we have plenty of them. Every few months, we see a new, powerful type of agent or harness being developed that tries to address these problems and provide proof of existence that the solution exists. But that creates a lot of fragmentation. These harnesses are actually very hard to develop. You need to have a lot of expertise. Now, we are clearly in the experimentation phase. And when you look at the history, we see that in the previous waves of innovation, the same thing happened. At the beginning, we have multiple versions of Unix. When container and cloud-native era started, we had lots of versions of containers, lots of container orchestration platforms, and entire divergent ecosystems around that. But eventually, the industry has identified common patterns, standardized on them, and consolidated. So we ended up with Unix and POSIX semantics in the first wave, and the Kubernetes and the ecosystem around Kubernetes in the second wave. We believe something like this will need to happen in the AI era as well. So that's what we in my research group are exploring. And the way we approach it is by looking at the types of agents that we are running in our organization. And we essentially have three types of agents. We have those that we have implemented ourselves using some framework or some SDK, so we have complete control over them. We have agents that are well-known harnesses that we can control via hooks and plugins. And we have black box agents that we cannot do anything about. Those we can only control by observing them on the outside. So what we are building is a layer of interception that can integrate with all of these styles of agents and provides a uniform a way to observe and modify all interactions that these agents are making with the external world. Using that layer of abstraction, we are adding control functions to manage how agents are behaving. Our first first problem that we've tackled has been security, and particularly the zero trust security, implementing multi-tier, multi-layer permission system to control how agents are, what agents are allowed to do. This included implementing agent identity, using that identity to implement delegation flows with authorization, then policy-based access, and then finally intent-based access to evaluate if what agent is doing is actually aligned with users' objectives. We have moved since to also start looking into the semantic layer of agents. So can we, in this business logic independent way, outside of agents, control the context and manage context that agents are using? Can we manage the correctness of tool calls and do data flow analysis to understand how data is flowing and control that? We are pursuing this in the project called Rosso CTL. Our web pages contain more information and also contain deeper results of various benchmarks and experiments. And my colleague Maya has a poster that she's going to present today, so I encourage you to stop by and learn more about what we have done. Now, crucially, we are not replacing the existing platform. All of the things that we are doing, albeit on existing cloud platform, we leverage existing standards and extend them. So standards like OAuth2, SPIFFE Spire for identity, non-policy languages. We are orchestrating this on Kubernetes. And our gateway-based approaches are originally based on Envoy proxy, but now we are moving to a more efficient Rust-based proxy implementation based on project Praxis. We have encouraging results. We can demonstrate cost reduction even with state-of-the-art agents from context compaction. We can demonstrate consistent improvements to tool calling accuracy, which translate into improvement to agent quality, and we can certainly demonstrate that we can transparently do permissioning for these agents. Another important part of the evolution of the platform or evolution of applications is, of course, application patterns. And we believe that for agents, the right application pattern is serverless. Serverless pattern separates agent loop as a stateless component from a durable session log where the context is being managed, and execution tier provided by diverse set of sandboxes. We believe that leads to better resiliency, better accuracy, better performance, and better scalability. And again, we have encouraging results. We can save a lot on infrastructure costs, particularly for agents that are model bound. We can flexibly allocate sandboxes, so not all agents require most expensive sandboxes, and they can be quite expensive. And we can also reuse sandboxes for certain types of agents where security policy allows that. So to summarize that, we do believe there is a new wave of a platform that is going to be built. We've started on that journey. We are very interested I am very interested in talking to you about this, if you agree or disagree, and certainly if you work on any project in this direction, I would like to know about it, and we would like to partner with you. Thank you.
Alrighty, and now we have Tim Holken with Distinguished Engineer for Google. Speaking is Kubernetes good for agents, infrastructure solutions for agent-shaped problems.
Hello. Oh, there I am. Thank you all for coming out today. I didn't realize this conference was on a weekend when I signed up for it, so I really appreciate you all coming out instead of getting a day off of work. My name is Tim. You may be familiar with some of my previous projects, Kubernetes. If so, I apologize in advance. Given my background, I tend to look at this agentic AI problem as an infrastructure problem. I see it from the bottom up. The customers that I talk with come to me and they say, we've got these agents, and Goja, like your explanations of the breadth of agents is exactly on point. There's a million kinds of agents, but they all come to us with similar problems, saying, we need to run them, we need to run a lot of them, we need the efficiencies that we're not getting. Agentic workloads are very different from traditional applications, which is really, it's caused people to ask whether Kubernetes is the right platform to run these things. It warms my heart to see Kubernetes mentioned on other people's slides, but I think it's a fair question. And so given this audience, I'm not going to go too deeply into how agents are different. I'll touch on it just a little bit. I apologize for racing through this material. I'm happy to do it again in the halls or talk whenever, after we're here for the next 2 days. So let's look at a couple of the things that make agents interesting. Agents are very bursty. They tend to work in very short spurts and then go idle for a long time, minutes, hours, even days, weeks at a time. This means a lot of idle resources if you approach it naively. Agent workloads, generally untrusted. I think it's pretty well understood at this point. Because of that, they have to run in sandboxes, and we're always looking at new kinds of sandboxing. And they have to run single tenant, because you can't share a sandbox. That would kind of defeat the purpose. That means we miss out on a ton of opportunities for optimizations, specifically the amortization of overheads. And lastly, they tend to have humans in the loop, which makes them very sensitive to the perceived latency of these systems. Taken together, this kind of makes it problematic to run them on Kubernetes. Kubernetes was built for things that run for a long time and tend to be scale out, horizontally scalable, and you can amortize your costs. So before jumping to a solution, I'm going to touch on the state of the art, what we've observed at Google and in the Kubernetes world of how people tend to run agents on Kubernetes. And there's really only two patterns with a few variations. So first is the obvious way. So Kubernetes has this idea of a runtime class, which lets you define a kind of sandbox. And the default runtime class is a Docker-style container, an OCI container. But we also have runtime classes for gvisor and for micro VMs, and it is an extension point for Kubernetes, so people can do interesting research around that. Some event causes the need for a new instance of an agent. So for example, a user starts a chat session. This obviously requires instantiating their agent, a special dedicated single tenant instance just for them, and each of those runs inside of an agent, a sandbox pod. Now, there's some cost. Starting up a pod on Kubernetes is not the thing that Kubernetes does the fastest. It's not optimized for that. It's not built for that. It's fast, seconds usually, but that's not fast enough. And so depending on what that agent does at startup, it could take a long time. And we've seen agents that load runtime environments that can take 10 or 15 seconds or more. Browsers, like all sorts of things. Eventually, that pod becomes ready and the user can chat with it, and they send their message to the pod and it comes back, and one turn is done, right? And now what? So because pod startup isn't free, what people tend to do is they wait for another event. And how long should they wait? Well, that really depends on what your agent is doing and what the startup cost was, and you have to do some math, and it's different for everybody. We've seen this range from tens of seconds at the low end to tens of minutes at the high end. And during those tens of minutes, your agent is sitting there consuming resources that can't be used by anybody else. Eventually, and of course this might happen multiple times, right? At 9 minutes and 59 seconds, the next turn might happen, and you start the whole process over again. So eventually you get a timeout and you're deemed idle, and either you're discarded entirely or we save your state somehow and then we terminate the pod, right? This is the standard Kubernetes lifecycle. Now, keep in mind this is happening for every instance of every agent for every user that is happening on your systems. There are tricks we can play with warm pools, and there's tricks we can play with suspend and resume. But Kubernetes doesn't support those things natively, and so you're kind of working around the system, and it's difficult to justify at this scale. The second approach is for people to build a DIY system on top of Kubernetes. Basically, this looks like a giant workload per machine. Inside that workload is a manager application. A bespoke control plane is responsible for scheduling things into that mega sandbox. The manager manages the lifecycle. Everything's opaque. Kubernetes doesn't know what it's doing. You end up reinventing large parts of Kubernetes. It's fairly complicated to build. It can be very efficient. It's difficult to operate for smaller companies, especially startups. Now, I'm a huge fan of open source. Maybe you can tell because I work in Kubernetes for the last 12 years. I have a deeply held belief that when it comes to infrastructure, open always wins. And so earlier this year, we set out to build something new that takes the best parts of both of these models, leverages Kubernetes where it can, because almost everybody has some Kubernetes in their fleet, and builds new components where we have to. Now, I'm not going to pretend that we've discovered anything new. We have not done any earth-shaking research here. What we've done is take some of the best ideas from all of our customers and our users and tried to glue them together into a way that everybody can use. In the same way that you put Kubernetes up on the slides as the middle box, I would like to fill in the right-hand second box for you. So Agent Substrate, and thank you for mentioning it, is a project that we began earlier this year. And have open sourced it. You can go to this URL, it'll take you to our GitHub. It's from a very high level, the model is pretty straightforward. We don't want idle resources. We want to use suspend and resume and cloud storage to multiplex agents onto pre-warmed runners and aggressively suspend and resume agents to take those 10 seconds to 10 minutes of idle and drive it down to a single second or even less. So let's talk about the goals. We're Google, so we tend to see things from the large scale point of view. We're shooting for very large deployments. We're looking at billions of sessions under management. We're looking at tens of thousands of activations per second, and we're looking at driving the wake-up time down into the low 3-digit milliseconds. Quickly, I'll introduce some terms. We have an actor, which is sort of a stand-in term for agent or sandbox or thing that acts like an agent. We have an actor template. If an actor is a cookie, the actor template is the cookie cutter. It includes details like what kind of sandbox tech, is it a gvisor or a micro VM? Notably, there can be many different templates inside of a single substrate. We have a worker, which is usually a pod running in a Kubernetes cluster. This is the thing that actually consumes resources. It waits for an assignment of an actor, and then it runs that actor. It can run many of them in serial, and a cluster can have many workers. And then 8lit is sort of our per node manager for all of the workers on that node. We need this for reasons around networking. And then lastly, 8net is our enlightened proxy, which will trigger wake-ups on receipt of traffic. Let's see how those fit together. Start with a Kubernetes cluster. Any modern cluster should work. We support running in kind, so you can run it on your laptop. The cluster admin deploys an instance of Agent Substrate, which includes an API server and storage layer, a controller which synchronizes data in and out of Kubernetes, one or more worker pools which create deployments, which create pods to run your workloads in, 8lits to manage all those workers, the 8net proxy which knows how to pass traffic from the outside world to the inside world, and then the substrate admin can create one or more actor templates. And the controller sees these and does some prep work. Specifically, it spins the actor template up, takes a snapshot of it, we call it the golden snapshot, stores that somewhere so we can use it later. Now, shifting view quickly to the substrate layer, which sits on top of all this, I'll warn you, some of this is aspirational, we're still working on it. We have our API server, router, and workers. Someone, a higher order system, creates an actor from that template. For example, the same chat agent. The chat app does whatever front-end work it needs to do, authorize it, whatever, and then it creates an actor. Note, creating an actor doesn't run the actor. In this hypothetical app, the user talks first. So the user sends a prompt, which is received and routed to the 8net proxy. It wakes up the actor, assigns it to a worker by sending a message through the router, and then talks to the worker on a private connection. Since this is a new actor, it wakes it up from the golden snapshot. The 8net proxy forwards the message on to the now running actor. And the cool part is this happens in a couple hundred milliseconds, and we're working on that optimization still. As soon as that turn is done, the actor is probably idle, so we can tell it to go back to sleep and suspend it. We call it pause. It can be paused, take the snapshot, and shuffle the data off, and now the worker is unassigned. It's available for use by another actor. All of that can happen as fast as your API operation or your agent transaction happen. Again, if another prompt comes in, we'll start the cycle again. And eventually, no more messages are received, and we will shuffle the data off to cloud storage, and it'll go to sleep for the night. Looking at the whole thing from the highest level, a Kubernetes cluster can be a one-node cluster on your laptop, or it could be 200,000 nodes in the cloud. Each of those nodes can run multiple workers. Each of those agents are idle 99.999% of the time, so you can do the math and see we're driving up to those billions of numbers. Agent Substrate is an open source project. It is still pre-production grade, but we're working really hard to get it out into a workable state by the end of this fall. And come take a look at it if you're interested in it. Take a look at what we've done. Bring us your feedback. The most useful thing that we can get from people is experience and requirements and context about what you're doing with agents. We'd love to hear from you. Thank you, everybody.
Thank you for the fantastic set of talks. We now are going to have a workshop on why your agent needs a wallet, agentic commerce on Arc with USDC and nano payments, with Harshal Bengali leading the way. If you'll allow a little bit of time to get the session set up, we will be underway in just a minute or two.
Good morning, everyone. Nice to see so many of you here on a Saturday. Yeah, really excited to showcase the work that Circle's doing in the agentic AI space. So my name is Harshal, and I'm a staff software engineer at Circle. So oftentimes, when I'm meeting AI developers at meetups and conferences, I get asked this question. So you're with Circle. Isn't Circle a stablecoin company? Yes. And why is what's Circle's role in the agentic AI era and agentic AI space? It's a fair question, but the answer is fairly straightforward because Circle issues USDC, and USDC is the world's largest regulated digital dollar. And turns out that the thing that your agents get stuck at is payments. And we have spent many years making payments faster and cheaper. And this is the gap that we're sort of going to look at today in this workshop. So when we often talk about making AI agents powerful and autonomous, we are thinking of powerful models, more tools, better quality evals. And those are the right things to look at. But one of the things that happens is these days, the models are strong enough that they can plan your task for you, they can write code for you, but the moment they face a paywall, or the moment they are asked to log in or sign up on behalf of you, they give the control back to you. And that's the gap. So what we'll look in this workshop, and I'd want all of you to participate, is how an agent is empowered the moment you provide it with a wallet and empower it with the ability to pay for it, all the things that it needs on the go, and how to do it in a secure way. So let's get started. Let's talk about how, let's see, issues with the slides. Let's start mirroring again. Yep, there seems to be an issue with the mirroring. So I think yeah.
Give it a second.
All right, awesome, thank you. So let's sort of look at where we were in a couple of years ago, right? In 2023, mostly we were interacting with LLMs via ChatGPT and just prompting. 2024, things got a bit more advanced. We started running some evals, getting a better understanding of how our agents work. 2025 was all about MCPs, skills, orchestrating agents, so having an agent manage a fleet of other agents and doing more powerful work. And in 2026, we believe that that's the year of where agents will go pay for things and pay each other. And the agentic economy is truly here, and it's about to stay. And the early numbers are quite promising. So if you look at the numbers, in the last 30 days alone, agents paid for $24 million worth of information on the internet, and 98.8% of it was settled in USDC. Now, when you think about just traditional finance numbers, 24 million is not a lot, but it's projected by 2030 that the agentic economy will be $5 trillion. And now the question is, why do agents get stuck? So let's sort of like look back at how the internet was built. So the internet, for the last 30 years, catered for one type of customer, which is humans. So all the payment rails, the monetization schemes, everything was custom made for this one type of customer, which is humans. So you had your sign-up flows, your subscription models, your paywalls, and ads, right? But now, there's this new type of customer, which is the AI agent. And the AI agent does not interact with the internet or behave in the same way as a human does. Their ability to consume information is orders of magnitude higher than any human. And you can prove it, right? Like you run a simple like deep research query with your Claude, and you'll see that like it's able to like read through like hundreds of pages of information in a few seconds. Now, some of those pages or some of those articles on the internet are behind a paywall, rightly so, because the merchants are like, okay, this is premium content, I want a human to pay for it. So once they hit a paywall, they can't go ahead and access it, and the quality of your research just sort of like is that degrades because it cannot reach that premium resource. So then on the other side, you have the merchants. And the merchants built these paywalls because they wanted to monetize content. But now they're realizing that there is this new customer base, and instead of like charging them a subscription fee, I can just charge a fraction of an amount for the agent so that they can just pay for that specific piece of article or that piece of data or some inference and make money off it. So why why not monetize this? And agents are increasingly, the traffic is actually going up compared to like humans. So there's this opportunity for merchants to monetize their premium content and resources. And they do that by just offering the same services for a fraction of a price for a traditional subscription. And that's the whole problem. But then you might ask, okay, why not just have my agent manage my subscriptions or give it a credit card? Well, it works. You could give your agent like a few subscriptions and API keys to manage, but does it scale? Because today you want task X, tomorrow you want something else, and how can you pay or subscribe for something that the agent just discovered as part of its research and is like, oh, I want to access this resource, I think it's valuable, and now it stalls. So that's the challenge. And then you can say, sure, like let's just use credit cards. Well, that's fine if you are okay giving your agent your credit card information, but the economics don't work either. Because as I mentioned earlier, merchants are exposing these endpoints or these resources to agents at a fraction of a cost. So if an agent, which is making these high-frequency API calls for premium content, has to pay 1 cent, and he has to, the agent has to like then pay 3% or 2.5% of credit card fees, the economics just do not work. right? So that's why traditional payment rails aren't the best way for AI agents to like pay as they go. What agents need is payments that work like the internet. Payments that are real time, low cost, programmable, and always on. And that's why Circle built the Circle Agent Stack. So it's a full stack platform for the agentic economy. And let's look at it by visiting agents.circle.com. And from here, like if folks have their laptops on, we can start sort of the workshop where we'll have like a few colleagues of mine over here who are probably collecting emails, and we'll be distributing some USDC for you to like try this as we go on an interactive journey where we try to like build a business. So let's see how our agents can, build something for us when they are empowered with a wallet. So let's look at agents.circle.com. So what's agents.circle.com? So you have a single place where your agent can hit a paid API. All you need to do now is just copy this prompt in one click and use your Claude, Cursor, or favorite like agentic coding tool, and then let it run. So it will install a CLI. It will generate a wallet. The setup instructions are very simple. My colleagues can help you out if you run into any issues. But let's also look at the marketplace, because I talked about agents being able to like pay for things as they go. But what do they pay for? What are the services? And then there's the question of discoverability. Like, how do they discover what services are out there? And that's where our agent marketplace comes into the picture. And the discoverability layer, so the CLI, once you download and set it up, you're able to, it's able to like discover these paid services. And you have around 1,000 endpoints from various providers spanning a wide range of sort of like categories, which is you have endpoints for image generation, for example, which just cost like 2 cents per image. You no longer need to have subscription for a specific image generation model. Then let's look at some financial analysis tools. You have like access to, for example, crypto prices and prediction markets. Prediction markets are fun. You can like have your agent, give it some funds and like make bets on the prediction market, and that's one thing. Social intelligence. So if you want to like plan some GTM motions or want to like do some sales motions, so how do you do that? Like just pay as you go for the content that you need. And it's one of the favorite things I use is the Reddit endpoint. So I'm just able to like query some Reddit information for just like 2 cents. And then there's your web search. So better quality web search for your agents for a fraction of a cost. So with that, if folks are ready, I'm gonna pause for a couple of minutes here. So if folks want to like start the workshop with me and install the CLI, and then we can take it from there. All right. Cool. So let's get started. So yeah, the first prompt is fairly basic, which is, okay, I want to start a coffee roastery in San Francisco. So can you come up with 5 names and look, if I want to build a website, I want to know if the domains are available. So let's see what our agent without a wallet on the left-hand side does and the agent with a wallet on the right-hand side. So you'll start seeing that the results, as we start doing slightly more complicated things, the results will show a difference in quality. So let's look at this. So the left-hand side one is just running through WUIS to see if the particular domain is available. And on the right-hand side, you can see that the agent is first checking whether there are funds, what's the budget, and it's making API calls to the via the Circle CLI, listing the wallets and checking the balance, and then is looking through the marketplace to see what endpoint do I have to essentially look for domains. So you have one which is stable domains, and it's the description. It was able to browse through the marketplace to see what matches my requirement, and now it's because it matched this description, it's actually inspecting that, and now it's going to give us the result. So you can see some domain is already taken. So it's all the left agent already finished. So yeah, obviously it's flagging that there could be some IP issues with Carl and everything. So we'll wait for this agent to finish. You see this agent actually made an API call for 10 cents, sorry, 1 cent to check if the domain actually is taken or not, and how much it's going to cost to actually purchase an available domain. So this information, I think you can find the same information with a free web search, but it's not as accurate, obviously, and this one is definitively true, okay, because it was able to query a registry and figure out, okay, it needs $20 a year for me to purchase a specific domain. So let's, okay, it's picking Sutro roasters. So I'm just gonna give it and say, let's go with, I like Pay Rise Coffee. I'm hoping and I'm just gonna copy it here and let the two agents run. So once that's finalized, the second task I want to do is, okay, now I essentially want to know the competition. I want to know, it's essentially a task about market research. So what do I need to do to stand out amongst my competitors? And I want some quality access to some journals and how to roast the best beans and which beans to import and some information like that. So that's my next task. So let's start with that. And I shall, so yeah, it asked a follow-up question, which is okay, check for trademarks, etc. So I'll just say this for now, and let's start. Yeah, also the other thing I did was I've updated the Claude.md file from in my agent over here to always give a very specific summary for the as part of each step here, so that everyone understands what happened and how much was spent as part of that particular step. So if you see it spent 12 cents total. So let's begin the next task. Any questions thus far? While the agents run, I'm happy to take any questions. Oh. Hi. So again, on the left-hand side, the agent is just doing your regular web search, and it's finding everything that's available on the internet for free. On the right-hand side, it's the agent specifically calling a Google Scholar API and then figuring out how to actually fetch those paywall articles, find quality research, and yeah, take it from there. Yes. Oh, sorry. Yeah. 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 Yeah, that's a great question. So we right now curate our marketplace with, so we are actually like looking at the endpoints and testing it out to ensure that, the marketplace, it's not just like anyone registering their endpoints. And the other thing, you bring up a great point about security. And I'm going to talk about like security of your funds, right? I was talking about how you could potentially give your credit card to an agent, right? That's dangerous. With Circle CLI and Circle wallets, what you can do is you're not giving your wallet or your fund to your agent. You're essentially creating a wallet for it, for the agent itself, and it's their funds. So you're managing funds for the agent itself, and you can have a fleet of different agents, and you can assign specific budgets to each of them. And even now, in the CLI itself, you can enforce the max spends and limits on, hey, how much can I spend per session? How much can I spend per specific website? Or how much can I spend it in a day? So these are thresholds, and these are policies which are enforced cryptographically, and you can then be assured that your agent will act within those guardrails, and your funds are safe. So then you should be able to like freely fund your agent. I hope like that answers the question from the fund side. Sorry. Yeah.
Use like a formal logic or a formal verification mechanism at the back end to, I guess, for the guardrails and the verification aspect for such agents.
Are you talking with regards to like just spending?
Yeah, just managing the whole thing, basically. I mean, for example, you're running this prompt and
Right.
like the whole process of it.
Yeah.
What plan it generates, how it's verified, like how it's spending. I mean, yes, of course, spending is the final endpoint, but.
Yeah. So I think like this is obviously a question that we are actively working on. And also some of the things that I can talk about with regards to like malicious spending, again, is we have like blacklists, and you cannot like transact with like sanctioned addresses and stuff like that. With regards to like what the model essentially does, it's again like that depends on the model harness, and we need to like do continuous evaluations, and we are doing on our end like evaluations on how our skills and how we can better improve those skills that we provide to make like better judgments. So yeah. Question? Yes.
Yeah. So my son is in high school, and I
Yeah.
also give him a wallet similar to this, so
Yeah.
he doesn't spend my credit card directly.
Yeah.
But what I learned is you also need to teach him like the concept of money, and then
Yeah.
making money is hard, so he need to spend smartly.
Yeah.
So do you do any research for your agent? Like I know you have skills and guardrails,
Yeah.
but that's kind of like just setting the rules.
Yeah.
But what to spend the money, how to invest in there's multiple websites.
Right.
Which one has a higher value for return? That
Yeah,
kind of
so
thing.
right now I think we've not enforced like such sort of like guardrails or like rules into the CLI that look for the cheapest one or something. It's obviously like based on your use case, and it can the CLI is flexible enough where like you can sort of like add additional skills within your project and setup to sort of say that, hey, if you need to like spend more than like $5, like now we're nearing my budget limit, so like start looking for like cheaper endpoints, right? Like similar to like how you would like if your monthly AI usage is like coming to the limit, you resolve to like using cheaper models. So something like that. So you can always like do that. But right now we do not have like specific rules around like, hey, which one to select. You will actually like, as I was doing a trial run yesterday for this, and I was observing how the model was thinking, it did, in the next task, I asked it to like generate a logo, and it was able to like just make an intelligent decision saying, you're designing a logo for a company, so it has to be of great quality. So I'd rather spend on the more expensive agent, which is a good sort of like image generation model, than a cheaper one, because the price difference is just a few cents. So I think the agent is making that sort of like decision intelligently, and you can always like tune it the way to your liking. But I do really like the analogy that you gave of having a wallet for your son, because that is exactly like how I think of this as a mental model. Like you have sort of like your almost like agents that you're managing, and you're just like funding them independently, and in a secure manner. So yeah. So thank you for the great questions. Yeah.
Yeah, real quick, I don't want to take up a ton of your time, but have you considered opening up the ability to register idle GPUs and agents to pay for their own compute?
Yes, so there are endpoints actually which allow you to like pay for inference. So within the marketplace, so you should explore that. And if there are enterprises, if anyone's over here that wants to like expose their endpoints, we have folks at the booth here for the next 2 days. Please come talk to us. The marketplace will thrive when enterprises and builders understand that like you can monetize your content and resources for the agentic era. So yeah, but great question. Looks like I'm gonna just skip past the research, and looks like both the agents finished. And let's just do a quick read through. Like, okay, it looked at some scholarly articles, and it spent about 17 cents to generate this. I'm actually gonna just tell the agent to use the agent. So I had a couple of wallets and one ran out of it, so it's thinking that it's like nearing its limit, so it's spending. To answer your question, it basically like cut down some of the research because it was, nearing the budget. So because there's only like 7 cents remaining in my wallet, so I just prompted it to like essentially use the wallet with more funding. Now let's look at the task that I was suggesting in the earlier conversation that, I couldn't copy this. Let's design a logo for our roastery. So over here, what you'll see is the agent is going to now leverage a model which is specialized in generating images. And currently, my cursor setup does not have any image generation models. So what you'll see on the left-hand side is the agent will try to essentially come up with a logo using whatever skills it has, whereas the right-hand side model will just pay a few cents and call the appropriate specialist model and get a logo generated. So let's see how that goes. quick time check. Okay. So this is what the agent does. Again, it does an estimate. There's an estimate call which tries to estimate, hey, for my like logo, like what's the price? And it comes back like saying you need 6 cents for this. And yeah, and now let's wait for the image generation to happen. Okay, let's look at this agent on the left-hand side. It says, okay, it verified, whatever. I'll just ask it to, looks good, build the logo. And so now it just paid like 65 cents to GPT image 2. And because the image generation can take some time, so you'll see that the agent itself is actually just polling because you call the image generation API and then you wait for the result. So it just polled for a few seconds because it set a timeout of 240 seconds. And now that the agent has returned, this is the logo that it generated for, let's see, 65 cents. Why was that? And, yeah, I'm sorry, not even 65 cents. It's 6 cents. My bad. I've been like, I missed out on the cost there. So on the left-hand side, the agent is still, because it's not an image generation model, I think it will still come up with a logo, but it will take a lot of time and it will just sort of build an HTML thing, and we'll wait for it. And since the agent on the left has already completed its task, I'm just gonna go ahead and tell it that I want you to make a flyer for my launch. So do that. So embed my logo, build a flyer, and the next task that we'll do, and where you'll see that the agent without a wallet will fail, is I'm gonna ask it to just email me all the details and then give me a phone call and explain what the research was done. The regular models without a wallet just do not have that capability. And let's see if you're able to accomplish that in the next 10 minutes. While the agents are running, any more questions that, yes?
A non-related question. At Circle, with this infrastructure, are you guys also looking into the commerce use case, like let's say buying shoes using the agent?
We are actually, we are trying to work with enterprises again to sort of come up with use cases, right? Like we want to work with enterprises to educate them that, hey, there's a use case for this. Now if you're a shoe company, you could essentially expose or curate an endpoint such that an agent, I can do that from my own cursor. I don't really have to go to the website and do something. So yeah, we are encouraging and we are actually trying to work with companies that, and it's not just shoes, any entity, any commodity that can be purchased on the internet by a human should be purchasable by an agent, right? So that's sort of the end goal. Yeah. And yeah.
how does the payment collection work in the agentic flow? For example, are you guys like fully integrated with the ACH payment methods?
No. So we are using stablecoins.
Right.
Are you familiar with stablecoins? So yeah, the wallets, these wallets are crypto wallets.
Right.
And once you fund the wallet, you can on-ramp. USDC has many on-ramping avenues, so you can essentially like on-ramp into your wallet and then sort of fund your agent's wallet. And then the sellers, the way sorry, while the agent works, I'll explain like how this whole agent interacts with the other enterprises and other agents. So for the last like 30 plus years, ever since like the internet started, like with HTTP2, the authors of the HTTP protocol, they had envisioned that payments would happen over HTTP. So they had this status code 402 within the initial spec, but it was kind of like dormant until now because there was just no means to like do that. But with the rise of like blockchains and stablecoins, that has become theoretically possible because what can happen now is a seller can, instead of like preventing you from just accessing something, can return a 402 payment header and says payment required and provide the credentials or the details. And it essentially says, send me X amount of USDC on this particular like blockchain address. Now, the agent, because it has the CLI, is now able to interpret that and realize, okay, I need to pay 2 cents for this image generation endpoint, right? And now it signs an authorization. It's a EIP 3009 authorization, and which essentially says, I authorize to pay a specific address the said amount, and it signs it with the key, and attaches it and re-requests that same endpoint. And from there, once the seller is actually receiving that second request with that new header, it processes it, figures out, okay, the payment is made or at least has been authorized, and I can now release the said resource. So now, because these transactions happen on chain, they essentially get settled. So there's no ACH involved in this. Does that answer your question?
Yeah. So would these transactions can also be like integrated with the ADK or MCP from the Circle point of view?
Yes.
Okay.
Yes. Sorry, let's hope. Yeah, this is back. Okay, and oh, all right. So, oops, this is still not visible. Sorry, I'm having some.
Hello.
Yeah.
Yeah, here. So I have a question. So does this agent have the capability of memory for the cases like you ask a specific questions that needs a very specific rules or law to follow, and then you asked exact same question or very similar question, and it can retrieve and be reliable enough to generate the same or similar answer for the similar type of query?
Yeah, so again, that will depend on the agent harness that you're using. So if you are using, say, Cursor or Claude Code, it should just, and you're asking it from the same session, even if you're writing to the memory, like you're updating constantly your agents.md, it should be able to like look it up, because Circle CLI is essentially just, think of it as just another like connector on the buy side, right? Like just like you have an ability to query Google Docs using a Google MCP, Circle CLI essentially like allows an agent to pay for things. So the memory aspect and all of those are, again, a function of the agent harness that you're using. So your Cursor and Claude Code. Does that answer your question? Okay, so.
I have one more question.
Yeah.
You mentioned at the beginning the idea that agents will need high frequency settlement for the transactions and also a low cost that they can pay. I understand this is a POC, but how far are we from having these kind of capabilities in the payment layer?
Oh, I'd argue it's no longer a POC because as I mentioned in my earlier slides, we have like at least like around like 24 million plus in volume in the last 30 days itself. So the whole X402 protocol, as I was explaining, the way agents pay for these resources, you can go online and like if you see the volumes, they are increasing. Like it started like I think late or early last year, and now it has picked up. And even though like it does not have the same volume as traditional payment rails, it's a start, and it's a very promising start because now you're just able to like, and even on our side, I can speak for one of our customers recently, like, you know, they were able to like make request payments for 0.00005 cents. So it's like 5 microcents per API call.
But
so
the fee for settling that transaction
is zero, because because you raise a good point that an actual blockchain itself, like even on the most economical blockchains, the settlement fee or the gas fees can be a bit high, like compared to this like number that I just stated, which is like 5 microcent. So that's why we, as part of the Circle agent stack, we have also built another solution called Nano Payments, which is on top of, which essentially allows you to make these like low sub-cent transactions at high frequency in a gas-free manner. So what you end up doing is you essentially, and this is a bit more technical, but you deposit funds into the gateway smart contract, which is what we did here, and then from there, you're just signing these authorizations. And instead of like settling that authorization on chain directly, what the seller does is it calls Circle's endpoints, and from there, what we do is we immediately like look at the buyer's balance because the funds were deposited in Circle's smart contract, and we are able to like deduct and reserve that balance. And from there, we instantly like return in a few, like 50 to 100 milliseconds, a success or a failure based on the balance. And then we gather hundreds and thousands of these authorizations and actually batch them and net them together in a trusted execution environment, and then broadcast them on chain as one single transaction. So that's how we scale, and we actually like prevent like clogging the blockchain network with hundreds and thousands of these like very, very low sub-cent transactions. And I'm happy to like go deeper into this after the talk. Yeah. Great question though. So now that our agent, like I said, so the agent was able to like make a fairly good flyer. Now I'm just gonna ask it to email this and give me a call on my phone and just like walk me through the research that it did, and let's see what happens. So and let's see if the call goes through. So let me just combine the final two prompts in the interest of time, and I hope like this essentially like gives people an idea that if you've equipped your agent with a wallet, there's a lot of possibilities that it unlocks. So, and we'll see like the agent without a wallet just say that it just cannot do this. So yeah, two things I can't do from here, which is send the email or place a call. So I'll hand you both as things you can execute in one step. So I had added my email and phone number as environment variable, so it's able to like fetch that, and let's have it run. And So the agent on the left-hand side is essentially just gonna draft something and then hand it over to me and say, go send this email. But the one on the right will sort of like go the whole route. So you see, like it says like stable email sends at 2 cents, stable phone at 54 cents. So let me check the schemas and see what I can do. Okay, it's running into one size. Okay, I'll stop it from. Okay, it's actually going to compress the image. So let's let it do its thing. And any questions I can answer in the meantime. Yes.
Thanks. I noticed you're running it on low and fast. Have you played with, like, someone asked about its understanding of money and budgets. Have you played with different reasoning levels and see what it does with budget and spending?
Yeah, that's a great question. And again, as you probably notice, it's like Opus 5 with low thinking and fast in the interest of time, because if you run it like with even like your regular models, it can take some time. So it's essentially, I tried to like do this the other day with, I think, was it Fable or Sonnet? So it built something so spectacular, but it took a really long time. So and for the lower, the other thing I also noticed was for some of the lower models, they are able to like make all of these calls just right, but sometimes it's just like the decisions and the summary. You can see the difference in like what it decides to call. So that's the difference you'll see. But it's just a CLI at the end of the day, and it can like say call that, okay, find me what can I discover, and then it's something that even the cheapest of models understand, right? So CLI being this age-old thing that every model actually understands. So okay, so looks like the email was delivered, and let me actually pull up my work email. Not yet. Well, let's check in a couple of minutes, but let's also wait for a phone call. And there you go. So now I'm going to put it on speaker. And hello?
Hi, it's your research assistant calling about Bay Rice Coffee. Got 2 minutes for the launch plan?
Yeah, sure.
Great. So bearscoffee.com is available for $20 a year, and your logo and launch flyer are already in the inbox. The differentiator is development time, not roast level. A 2020 beverages
sorry,
paper found longer development gives more.
Can you actually just tell me? Can you just tell me which beans should I buy? Should they be, and from which roasters? I just need that information.
For sourcing, Royal Coffee in Oakland has Crown Jewel micro lots at 22-pound boxes, $220 to $455, about $11.60 a pound green.
Great. And did you actually send?
For the core lineup. Go ahead.
Yeah, thank you. And I'll just grab the rest of the information from the email. So thank you so much.
Sounds good. Do you want me to register the domain or run a trademark check before I go?
No, I think that should be all. Thank you so much.
All right, talk soon.
And that was, yeah, that's how like you can essentially like equip your agent and make it more autonomous. So yeah, that was the end of the demo. And I do want to like still see like if the email landed, but if not, let me just show you an email from a dry run. I don't know if it is in my spam, but yeah, there's a dry run email that I had earlier this morning. So yeah, so with agents.circle.com, the final pitch is, yeah, if you are a seller or if you are an enterprise that wants to actually build, you can, as a developer, even like wrap and monetize your endpoints in just a couple of lines of code and list it on the marketplace. And yeah, this is just the start. There's a lot more to come. And if you found this useful and insightful, please come talk to us. We are here at the booth. We have a booth. Yeah, and that was that. Thank you so much.
All right, and now it is time for lunch, and we'll have speakers again at 1:30. Enjoy the lunchtime.